All right, this is an interesting paper that came out pretty recently, and it talks about the problem with scaling transformers to large context windows. Um, and I already talked about rope, which is a method to have relative embeddings, but the problem with rope is it doesn't do well at extending beyond the range it was trained at. Um, yeah, so go and check that out. I already talked about that, but yeah, let me just I'm briefly talk about rope and positional encodings, but I'm going to assume you have knowledge of how a transformer works and of how positional encodings work, because this paper kind of goes into how to fix the extrapolation problem, and it does so pretty well. So you have your sequence with the transformer. Say I love cats. I love cats, and this is your sequence, and you throw this through a transformer. And the problem with the transformer is if you, it only works on sets and unordered sets. So this is an unordered set right now. So what I do is I add positional encodings to each of these, which basically tell the transformer where is this part of the where is this token at in the sequence. And to do that, you can use either sinusoidal absolute embeddings, or you can use a method called rope, which does rotary embeddings. And the way rotary embeddings work, the reason I'm talking about rotary embeddings is that's what they mainly discuss in the paper. But I think it can actually be leveraged to do any type of positional encodings if you can use their method for that as well. But they specifically talk about rope. So what rope does is it says what is the relative location of a token. So in this case, it would say, it would make, I mean, the goal of relative positional embeddings is to kind of create a matrix. In this case, it would be a 3x3 matrix, which kind of looks like this, where this would be like 1, this would be 2, and this would be -1, -1, 2. And this is your attention matrix. So if this was I love cats and I love cats, then the relative position of each of these tokens is encoded in this matrix, where the 1 basically says I'm 1 position away from you, and in this case it says I'm 2 positions away from the word I, and so on. So you kind of want something that kind of looks like this, because this gives you your relative positional information relative to each token. And like with the word love, the word I comes before the word love, and the word cats comes one after love. So that's why, and that's how you embed it using a matrix that looks like this. And the way they do it with rope, with rotary positional embeddings, is through dot product. They leverage the dot product similarity matrix, and they use rotary. They use rotation to embed that. So if I say, for example, I had let's say the token I, or let's just say we have a token in 2 dimensions, and the token is a vector at 1, 1. So in this case, it would look something like this. Then the idea of rotary positional embeddings is I'm going to rotate this vector a little bit for position. So this would be the blue vector would be the second item in the sequence. And then I'm going to rotate the sequence, or I'm going to rotate the vector a little bit more, and that'll be, say, the third item in the sequence. Yeah, well, it wouldn't be 1, 1, it would be -1, -1. And in this case, it would be -1, 1. So in this case, our sequence is, I guess this would be I, love, and cats. But since they're all represented by the same vector, this would be the sequence I, since they're all the vector 1, 1. So if you had the sequence that's 3 tokens that are the same, then you rotate the vector. In this case, we rotate the vector 90 degrees, and that tells you basically, and if you rotate it 90 degrees, then this vector is different from this vector, and the rotation gives you, it embeds the information of the position. So if we have a sequence that's 3 tokens long and they're all the same token, then it'll just rotate the token a little bit in each direction, and it rotates it like normal using a rotation matrix, which I talked about in the rope video. But yeah, it'll just rotate it. And if we take the dot product between these to create our dot product matrix, so let me color code these. So that's I, and that is I. And then we want to create our matrix, our 3x3 matrix. That would be I don't know why, but I mean, yeah, there, that's fine. They're the same token, but yeah, in this case, the dot product similarity would be, it would be a 1 here, and it would be a 1 along the diagonal because the dot product with itself is a 1 if you normalize it, and then the dot product of, say, this vector with this vector would be 0. So it would be a 0 along this diagonal here, and like the dot product with the blue vector with the red vector is also a 0. And it's the same the other way as well. If you take the dot product with the blue vector with the black vector, since the order you do the dot product doesn't matter when you have 2. And then in this case, it would be -1 for the last one if you do the black vector with the red vector. And you can see this basically gives us our matrix up here, except if your angle, you're going to use an angle that's smaller. So it's basically a normalized version of that. And you kind of inherently embed the positional information by doing it with rotations as opposed to doing it with some other way. Absolute embeddings is where you do the sinusoidal sampling method, where, say, I have this matrix here, and at each point I do a different sinusoidal path where 1 is really slow, 1 has a lot higher frequency, and then another sine wave has a really high frequency. Then token 1, 2, 3, 4, and 5. So this would be like I love cats and so on. Then you would basically just sample these waves at different time steps, and that gives you pretty much, and that gives you a unique positional embedding for each of these tokens. So this is your absolute embeddings, and these are your relative. Now, and they deal with relative in this paper. So the problem with these is it's a lot easier to show with these embeddings, but the same problem exists with the rotary positional embeddings. But the biggest problem is if I only train a model, say, on 3 tokens, then it only sees the positional embedding information for the first 3 tokens. And obviously there's more positional information as you extend your sequence to a longer number of tokens. But since the model was never trained on that, it doesn't know how to deal with longer sequences than 3, and it starts to go crazy. They show here in this diagram where if I train a model on, no, I don't want that. If I train a model on 2048 tokens here, but then you can kind of see in the range from 0 to 2048 to 2048, then the attention scores are pretty normal, in between -1 and 1, as you would expect, because our dot products are going to be in between -1 and 1, and maybe you scale those a little bit, but because of the softmax, I'll scale them differently. But yeah, your attention scores are between -1 and 1. They're very, or I guess between -3 and 3, but they're they're small numbers. They're easy for neural networks to deal with, and they look pretty regular. And that's what you see here. But once you go a little bit beyond 2048, say 2500 or 20500, then you start getting values that are kind of crazy. And if you go past 3000, you get an attention value of 8000, and that is basically going to make your network give garbage outputs. Like this, nothing is going to be useful with this information. And that's the extrapolation problem. If I go out beyond the length the transformer was trained at, the sequence length, then you're going to have issues. And usually you only train on a small sequence length because, remember, a transformer is n squared, where n is your sequence length, and the attention matrix has to be that large. But also, so it's n squared in terms of time, to compute this matrix, and in space. Space used to put that matrix in memory. So you can only train on a small you can only train on small number of on small sentences. So you usually set like a cutoff limit of say 2048. But whenever you're doing inference here, you probably want to go longer than 2048 tokens. And remember, a token isn't a word. It's a part of a word usually. You usually do word piece or byte pair encodings, and that makes your context length even smaller than you would actually want it to be. So usually you want to go beyond the length at which the transformer was trained at, and that's what this paper does. What it basically says is, if instead of looking at, so if we train with only these 3 tokens, or let's say we have a sequence that's say 6 tokens long, or say we only train on a sequence that's 3 tokens long, and then we have our sine waves that look something like this. So that goes a little bit faster, and then that goes even faster. And you sample them like so for each of these tokens. And your model's only trained to know this context window. But say I have a sequence that's 6 tokens long. What you do is instead of sampling out this way, you basically interpolate this. So instead of making position 3 in your sequence, you're kind of going to squish it. So instead of they show it up here. So you're gonna kind of squish the sequence. So this is your unseen range, and this is your trained range. And notice how they kind of squish the points. So say this was your first point here. This is your second point. This is your third point. But then I want to train on a sequence of 6 points. Then your first point would be here. Your second point would be here. And notice how the first point aligns with the first point pretty well. Like your first point aligns with the first point. But then the second point in the trained sequence aligns with the third point in the sequence you're trying to generate. So what they did here is they basically doubled the context window, because you are sampling your trained range of positional embeddings twice as frequently as you did whenever you trained it. So you train on this range up here, and you sample it more. So you'll sample there, there, and there whenever you're doing your inference. And this way, your model knows this range here, so it knows how to deal with these values. And since it knows how to deal with those values, it's not going to see some value and give some massive 8,000 value because it's never seen this value and it's not in the range of because it wasn't trained on that. So all you're basically doing is you're squishing these embeddings, and the way they do that is through here. So if our positional embeddings are given by f, make this black. So if our positional embeddings are given by f of x ml, if they're given by x, so you have your sequence, and then you have the location of the item in the sequence, that is m. So that could be like 0 or 1 or 2. That's your location in the sequence. Then normally, then f would normally be in the range of 0 is less than m is less than, let's say, 2048. Well, L is equal, or is less than L. And in this case, they say L is equal to 2048, and that's our context window that we train on. But let's say we want to extend it to say L is equal to 40, what is it? I had 2048, I cannot, 4096, is that it? Yeah, 4096. So let's say I want to extend this and I want to double our context window, but our original transformer was trained on a context window that is only that only has a context window of size L. But what we want is we want an M which is between L and L prime, or between 0 and L prime. So the idea is, well, we want to interpolate between the embeddings we already have instead of extrapolating beyond the embeddings we have. So normally, in the bad case, you would say, oh, okay, I'll just add more. So if I want to have a sequence length of say 3000, then I'll just make that 3000. But what they do is they say, well, we can interpolate, or instead we're going to interpolate this using this formula here. And the formula is ml over L prime. So in this case, if we had, say, m is equal to 0, then we would have, then say m prime is equal to 0 times L over L prime, which is equal to 0. And if m prime is equal, and if m is equal to 2048, then you would expect this to be kind of half that. And if L is equal to 2048 and L prime is equal to 4096, then you can see that this part, that the L over L prime part, is going to be equal to 1/2. So you're basically going to scale m by 1/2, and 2048 would become 1024. And then if m is equal to 4096, then your m prime would be equal to 2048. So you basically are just scaling this down by a factor depending on how much you want your max context length window to be. It's a very easy and intuitive formulation to kind of extrapolate your embeddings, but you're extrapolating the embeddings by interpolating the embeddings in the range it's already seen. And they show here that as you increase your length of your sequence, but if you sample more often, then the range of values is very stable. It's not massive, it stays within a good range. So if you instead interpolate your values, then that's very helpful. And it keeps the attention scores relatively normalized. Now, you do this after training, so your first thought may be, well, if I do this after training, how does that affect the value? How does that affect the output? Does it make them worse? Does it make it, how much worse does it make it compared to if I were to just extrapolate? And that's, now we don't want to get into the results because the implementation is very straightforward. You're just scaling your relative embeddings down by a factor. So instead of having m is equal to some value, you do some interpolation. And before I go on, I kind of want to show you what this looks like. So in the case of our example up there where we had a vector 1, 1. If we scale this by a half, then this would kind of move it by 45 degrees instead. Kind of. It's easy to visualize that way if we do that. So it'll rotate the vector by 45 degrees. And then, so remember we had 3 vectors in our sequence. It was 1, 1, and then you had then you had another vector that was perpendicular to this vector, which was right here. But instead of rotating it 90 degrees, you're going to rotate it halfway, so it'll be 45 degrees. So in this case, it would be 0, 1, and then you rotate your third vector 45 degrees again. So that'll be your negative 1, 1. So instead of your sequence being 1, 1, negative 1, 1, negative 1, negative 1, you rotate them slightly less. And since your network knows the range from, say, here to here, it knows that range, then it also knows the range in between. And that's the idea behind this paper. You're going to rotate them slightly less as opposed to rotating them more and more. As if you were to extrapolate, then it would rotate it here, then it would rotate it again, and then it would rotate it beyond the range of training, which was this vector, which was the third vector, that was 180 to this vector. And that's the idea, just rotate slightly less, just sample more along the values you've already seen, along the values the network has already seen. And the idea is that'll make it more stable. Now let's see the results. Does this actually make it more stable? And the answer is yes. That's why they wrote this paper. So if in this first example, they evaluate on this data set here, the PG19 data set. I don't know what this data set is, some benchmark. And they show if we have a context window of 2048 and we don't use any method so we basically take our base model. I think they use llama. So they take the 7 billion llama model, and all they do is, so the llama model is trained on a window size of 2048, context window of 2048, as seen right here. And if you just scale that up, you can see that the perplexity is massive. Like the perplexity right here, 10 to the third, it just greater than 10 to the third. Like it's basically outputting useless garbage that doesn't make any sense. But if you use their method where you do the positional interpolation, then you can see, even though it was trained on a size of 2048, this is the context window size. Then this is the context window size due to the interpolation. So this would be our L prime. Then you can see that the perplexity actually goes lower as the context window size increases. And the reason the perplexity goes lower is because it can use more information. If you have a larger context window, then it's able to pull more information from previous parts of the context. But since it's actually decreasing instead of increasing, you know that it not only can use the previous parts of the context window, but it also does use the previous parts of the context window, meaning that it's able to pull from, or meaning that it actually uses the context window. Even though it has this context window to use, it still uses it. And you can see they also do this on 13 billion, and it does really well. And it shows the same. Now on another data set, it shows the same, where I guess they don't evaluate it at all here. But yeah, it shows the same. It shows the same trend here, where it decreases as you increase the context window size. Now another thing to point out is, well, how does this compare to, say I have a sequence length of, say I have this data set here, and this data set is composed of sequences that are 2048, and I train my llama model on that, so this is llama sub 1, And then I take this llama model, and then I have a smaller data set of 4096. And then I fine tune the llama model using the normal extrapolation method. So I using this normal extrapolation method up here, where you go beyond the sequence length. How does that do? Would that make, since it's able to see the range that it hasn't seen before, does that make it better? And this would be probably your immediate thought whenever you want to extend the context length. And they show, well, kind of, like it still retains the information. So in this case, they fine tune the llama using the extrapolation method, where you don't do the interpolation method that they proposed, but you just keep increasing the context window and you keep increasing the positional embeddings as they showed above. And you can see it doesn't, although it has this context window, it can't use it because the perplexity is increasing. And higher perplexity means it's doing worse. But if you use their method, then it does work, where you do the interpolation method. So even though in this case, so if you look in between the normal fine-tuning extrapolation method and their positional interpolation method, and you can see it uses the context window because the perplexity goes down as the context window increases. But if you do the extrapolation method, it doesn't use the context window because the perplexity increases, so it does worse as the context window gets larger, even though it was fine-tuned to do 8192 context window length. And that just shows that the method of the interpolation method is a lot better. Now, you also have to fine-tune using their method. You also have to do fine-tuning using their method. And if you don't fine-tune, you can see the scores are really bad. So if you just do no fine-tuning and you just do positional interpolation, then the scores are really bad. However, if you do only 200 iterations of fine-tuning, then the scores are really good already. And if you keep doing fine-tuning, then they get slightly better, but with just 200 steps they use the pile, you can get this perplexity decrease. You can have it use this context window, which is very powerful because all you need to do is fine-tune on this larger data set for 200 update steps, for 200 steps, and you get this massive decrease in perplexity, and it can use this massive context window, and you can increase it to 3,000 or 32,000, and it still does really well. So this method is really powerful. It's really cool to see, and it's really simple to implement. Just fine tune using interpolation as opposed to extrapolation. So yeah, this is kind of a quick paper. It's not too difficult, and they do open source. They have some code down here, and to show how they kind of made the diagrams above. So yeah, it's pretty cool. I'm pretty sure this method is going to be used in the future because it's easy to implement and it is able to fix problems with current models that are already trained, like Llama or Falcon out there. I may test this out, and if I do, I'll put my results in the comments, since I'm kind of playing around with the Falcon model right now. But yeah, that is this paper, extending context window of large language models via positional interpolation. I will see you later.